class for the cosine? Okay, based on that series notation, I would like you to write the first several terms. What are the first several terms of this?
Hey, Gary.
Yes, ma'am.
Zach said that to tell you that you invited him to an event, but not the hangout, so he can't see anything.
What?
Events are the same thing as a Facebook style thing where everyone says they'll be there and no one shows up.
I don't understand Facebook, so that doesn't help. How do I get Zach in here? Shit.
No, he invited him to an event, but not the hangout.
Okay, I gotta look up what's the difference between an event and a hangout. Event versus hangout. Okay. M is our counter. First M is 0, then M is 1.
Oh, I'm sorry. M was 2N.
2M is N.
Oh, was it 2M that's N? Or not?
In the problem we were playing with the other day,
Yeah.
we let 2M be N. We set N equal to 2M last time.
Oh,
So I'm using M in a different way this time. Sorry.
You did write it down.
Okay.
I didn't.
Recommend how screen share, Q&A, capture, cameraman. Oh, maybe it's up here. Invite people. Ah, okay. I'm trying again. Zach and William.
how many turns did you want us to calculate?
Do 4, so my.bluecc.edu.
Me too. Yeah.
Ah, shit.
How rigid you like some guy named
Did you write these terms down?
Yeah.
Okay,
in my head.
excellent.
Like some guy named Richard was like, I want to be called Dick from now. That's the name of it.
You should look up the etymology of that. Okay, here we go. Okay, can you tell Zach I just tried to invite him, please? And thank you. I think I got it right that time. Okay. So let's see if I got this right. Oops. If M is 0, I get 1. If M is 1, I'm going to get a negative 1/2 x squared. If M is 2, I get a positive 1/4 factorial, which is what, 24? X to the 4th.
When we take the test, will you want us, is 1/4 factorial just okay?
It is sufficient most of the time. I did critique some of your tests where you were writing nice proper fractions, like using the calculator's fraction button, but sometimes it's better to look at decimals to kind of get a feel for things. I don't know if you see the notes, some of you I wrote that on. You should. Okay, I'm pretty sure that is the sequence, or the series, sorry, that we derived in class the other day by taking repeated derivatives. Okay, this is a Taylor series, true? Centered at? Oops. Yeah, centered at 0. Okay. did we get so far as to find its radius of convergence? I believe we did. But I'm not sure. It is infinite, yeah. So R is infinite. So that means this supposedly converges for all real numbers. It's my fancy R for real numbers. Now, this is an alternating series. So that means the alternating series remainder theorem applies to this. Alternating series remainder theorem, so I'm going to try and deal with supposedly. Yes, ma'am.
For the very first term,
Yep.
isn't it x squared?
In the first term, m is 0, right? Okay. All right. So we're good? Now, did we, I think we graphed some of these terms to see that it wiggled like the cosine? Right, okay, good. Other thing we noticed the other day, the cosine is an even function, which means it is symmetric about the y-axis. Excellent, yeah. And the terms happen to be all even in the polynomial. Right, okay. What does the alternating series remainder theorem say?
Must be positive.
What must be positive? That's the alternating series. That's the alternating series test. I'm just the remainder.
More than whatever you're
Yeah.
trying to beat.
The remainder is going to be less than or equal to the next term in line. Okay. All right, so let's see. Our remainder then is going to be less than the next term in line. Okay, what's the next term in line? The next term in line is all this stuff with an m plus 1 in it. Okay, now we're dropping the alternating part because we're looking at the u's, right? So that means the alternating series remainder theorem, come on, pen, applies to this part right there with an n plus 1 instead of an m. So that means I'm going to have x, oops, it's not a pretty x, let's just go with it. We're going to have x to the power 2 times m plus 1. That's cheery math, isn't it? Divided by 2 times m plus 1 factorial. That's lovely. I think it probably looks better on Google Hangouts. Zach has joined the group. Howdy, Zach.
Go home, Zach.
Okay. All right. Interesting. That part concerns me. What's x? Well, we have a radius where x, yeah, at any particular moment x is constant. However, there's infinitely many x values we can have between positive and negative infinity here. So x could be 100. X could be 1. X could be 0. Okay, so that x is a wee bit of a problem. Okay, so we have trouble here. Really? Crap. It says it's broadcasting the screen. It says my voice is going up and down. Huh. Ask if you can see my text in the chat box. Let's see. Well, it says William and Zach are there. Oh, William can see it. Okay. Can you see the screen too, William? You can see and hear. Okay, so William can see and hear, but Zach cannot. What happens if I click on Zachary's box here? Oh, I get Zach's screen in charge. Hi, puppies. Okay, that's back to my screen. Okay, so I can switch whose desktop we're looking at. That's interesting. All right, I am not sure. Zach. Oh, interesting. He's ask him if he can click on my face. That might help. He should see all of this. What if I reset it? Screen share off, screen share on. Okay, I reset the screen share. Sorry, William, we're having technical difficulties here with Zach. Hopefully we can resolve it. And as my technical assistant, I owe you for that. Thank you. Yeah, you have his number? I can call him. Hang on, it takes me a second to get there. 541 2561. Yeah. Okay. I got his messages. Maybe he doesn't recognize my number. Oh, Zach's back on. He's on twice now. Hey, Zach, this is Gary Parker. This is my cell phone number, so now you have it. You can call me or text me. Hopefully we're going to get you connected soon. Talk to you soon. Bye. All right, let's do a little math where we see if Zach can get back in. Okay. So, X is troublesome. We got to do something about that. So we got to figure out what to do with the remainder. Unfortunately, Taylor thought about that when he had developed these series, and he has what's called the remainder theorem. And we still have Zach there twice. If I click on this other Zach, 5 points each except the last one. 10. Yeah, that was worth 10 points. Okay. So Taylor's remainder theorem says that the nth remainder, it's a lot like the alternating series theorem, is going to be equal to, or less than or equal to some number m, we'll talk about m, times the absolute value of x minus a in absolute value to the n plus 1 over n plus 1 factorial, right? Yeah, after class, sorry. Okay, so what does that look like? Does that look familiar, Taylor's remainder theorem? Actually, it looks like the alternating series remainder theorem. Yeah, so it's a tweaked version of the alternating series remainder theorem. It's like an extension of it. We had to make the alternating series remainder theorem a little bit more powerful, and this does it. Now, what's the m? The m is some special maximum number, and it has to do with the n plus 1th derivative. Come on, Blue, there we go. So our m has to be less than or equal to the n plus 1th derivative evaluated at some special number c. And c is between a and x and a. The number c has to be between x and a. So basically what we're trying to do is we're looking at the nth derivative, or the n plus 1th derivative, because that's the next thing in line that gives us the coefficient. And we have to say, okay, can I set a boundary on this derivative? And most of the time we can. Okay, so that's what we're going to do next. So we're going to do that for the cosine. Okay. So let's think, what do derivatives of the cosine look like? So n derivative of the cosine of x, right? The derivatives are either plus or minus cosine or plus or minus sine, right? Okay. What do all those sines and cosines have in common as far as some kind of upper bound? Yeah, they all stop at 1. So we just found a value for m. So m should be 1 here. Let's see, Zach came and left, and he's still got an old version here, so he's probably still having trouble. All right.
He said he'll just watch the recording.
Okay. Bummer. Sorry, Zach. That didn't work.
So, is m always the upper bound?
Yes, m is the upper bound of the n plus 1th derivative. We have to figure out how to establish that. Okay. Now, cosine is nice because it wiggles, and it has a specific number it doesn't wiggle above. If we were playing with e to the x, it's a problem because it rises forever. So what we have to do is just say, find that you rise forever. I'm just going to stop you there, which means I can't look beyond this x value. And we'll do a problem like that later. Okay, so sometimes the upper bound is obvious, sometimes it's not. You got to fiddle around to get it. And once you pick an upper bound, that will limit you. So in this case, this bound, if this were e to the x, limits the x's we can use. We couldn't use an x beyond this point right there. Okay, it's just the way it works. And I can show you a picture of why that works the way it does in a minute. All right, let's get back to the cosine. So with the cosine, we know the cosine of x is equal to 1 minus 1/2 x squared plus 1/24 x to the 4th minus 1 over 6 factorial x to the 6th, dot, dot, dot. Keeps on going. Now we have a boundary for the nth remainder. It's going to be less than or equal to 1 times the absolute value. What's our center again? 0. So x minus 0 is still x. Now the next term for the cosine is 2n, or m plus 2 over 2m plus 2 factorial. All right, double check. with our pretty picture way back here, right? 2 times m plus 1 is 2m plus 2. All right. We're getting there. Is that the right page? Yep. Now, we are still exploring the idea of this supposedly converges for all real numbers. Okay. So for a Taylor series to converge, the nth remainder must go to 0 as n grows. If the remainder, if that tail doesn't shrink properly, then the series is useless. We don't have a convergent power series. For whatever x value or x, now that the question here is x. Some places series only converge for a single x. Sometimes x could be between -1 and 1. Here we think x can be any real number. So we have to explore what is the limit as n increases of the absolute value of my remainders. So I have the limit of an infinite series here, which is rather complicated. Right? This is really the limit as n increases of the sum as I goes from n plus 1 to infinity of whatever my, in this case I have what my terms are, -1 to the I over 2i factorial times x to the 2i. So that's what the nth remainder is. It's an infinite series. It picks up wherever you left off and it goes forever. Sorry, I have to. Okay, shall I call it k then? I'm going to use k then. So that's a k there, that's a k there, that's a k there, that's a k there. Okay. Well, the book is going to read I. Hopefully you're reading your book. Okay.
Thank you.
So, but what's the advantage we have here? We know, according to Taylor's theorem, that our remainder has to be less than or equal to that nice little thing, the absolute value of x to the 2, I'm going to use n, sorry, plus 2 over 2n plus 2 factorial. So since I'm taking the limit of the left side, I have to take the limit of the right side.
Oh, okay, so that's less than or equal to that.
Taylor's theorem says that this is less than or equal to that.
Okay.
So if I take the limit of each side, it still holds.
You're not gonna make me say Taylor said so.
Now, what do you like better, the red stuff or the blue stuff? I like the blue stuff. It's not, because an infinite series is a limit, so basically the red stuff is a limit of a limit, which is rather painful. But the blue stuff is just a simple limit. We've done stuff like this before. Now, Jeff made a point before that at any instant, x is fixed. So x is a constant at the moment. What's happening as n increases with this limit? As n increases, what is this thing going to? What's the denominator? Yeah, the denominator is getting bigger and bigger. It's a factorial. The numerator is stuck at whatever x is in that instant, and so this is going to 0. This is like, by the way, this is like one of the easiest Taylor remainder theorems we can do. Well, Taylor's remainder theorem applies to any power series generated with derivatives like we did the other day. And there's infinitely many of those. And this is one of the easiest ones that we can do. It's not the easiest, but it's in there. Why is this one easy? Because the boundary on the remainder is easy to find, and it's 1. Yeah. Yes. Right. Finding the boundary is the hardest part. Yes, there are homework problems. This is section 10.9, maybe?
That's how many homework
10.9. How many more homeworks are there? 10, 7, 8, 9 has been assigned. Yes. Yes, but I haven't used the word Maclaurin.
Oh, we have learned it.
Yeah, a Maclaurin series is when we're centering it at 0.
Centering it.
Yeah.
Okay, 'cause I got really
Yeah,
Can you
Maclaurin.
go to view an example and just kind of work through?
Yeah.
That makes sense.
So basically, the big thing is everything is a Taylor series that we're talking about. If- Yeah, because if you make Taylor series centered at 0 like this one, then some people call it a Maclaurin series. And our author likes to call them two different things. I don't know.
Studied the same thing at the same times.
Okay, so yeah, they did, and
No one knows who to give
Yeah.
credit to.
it's easier to spell.
Like,
Okay, so what have we shown? And yes, by the squeeze theorem. So by the squeeze theorem, so last page, by the squeeze theorem for limits, the Taylor series for the cosine, where does the series converge?
0
We don't know.
in between the functions.
For all products?
All real numbers, yes, for all real numbers. That's what the ratio test shows us. For all real, we did that last class, numbers. Okay, whew. That was wicked exciting. All right,
I'm kind of assuming that some of these fancy problems will be on the take-home portion.
yes. Yeah, these remainders on Taylor series are quite challenging. All right, new problem. Review from last quarter. I would like you to integrate the sine of x squared. Oh shit.
This is the X squared thing.
Why is x squared a problem?
Because there's not an X on the outside.
Oh, so you're thinking u substitution, right?
You can't use U substitution because there's not an X and you can't.
Okay, so let me do that.
Can you reverse substitute though?
So u equals x squared implies
So solve x squared for
du equals 2x dx, right? Which means to do a u substitution, I need an x on the outside, and there's no x on the outside. Okay.
Why
So-
can't you say the square root of u equals x?
Because you're trying to get rid of all the X's.
We could do that, so that gives us the square root of u equals x, provided that, let's see, u is greater than 0, right? Then that doesn't change this.
Well, can't you substitute that in? Put an x in there.
Okay, so we can do that. So that comes down here, and we get the sine of what? The square root of u squared, which is u, right? And then instead of a dx, that would give me, I'd have to move this 2x underneath the du. So I'd have 2u over du over 2x.
It doesn't work. Then you still have.
Now I have x's and u's.
We don't know how to do that.
Why don't you have 2x?
Okay, so x is the square root of u, so now we have the integral of the sine of x divided by twice the square root of u du. Nice work, Jeff. Huh? Well, you told me that x is equal to square root of u, right?
But you put sine
Oh, sine of u, sorry. Oops.
of it. Okay. Yeah. Ooh, that's
U.
fine.
Okay,
Yeah.
cool. Integrate that.
I don't know. I don't know if that works.
It doesn't. Okay, you can try integration by parts on that and it won't get anywhere.
I gave it a shot.
Okay, you did. That was a great shot. Okay, so all of the here's the problem. All of the integration techniques that you learned, are you Facebooking that? Please do. Thank you. Okay. All of the integration techniques you learned last time you took this Calc 2
Not apply.
do not apply. All right. Well, that's all right though. So In the second part of class that you guys skipped out on the other day, we developed a series for the sine of x. Now the sine, check this out, is an odd function. What that means is it is symmetric about the origin. Okay. Well, the cosine was an even function because it's symmetric about the y-axis, and coincidentally, all of the terms in its Taylor series were even powers. So maybe sine gets all the odd ones. Okay, so let's look back at cosine for a minute. Cosine, where'd you go? Right there. The first even power is 0. The second even power is 2, then 4. So the first odd power should be 1. Okay, so let's try this and see what happens, then we'll prove it. So I'm going to guess that the first, come on, maybe. There we go. I'm going to guess that the first term for the sine series is, it's probably just x. Okay. Then the cosine alternated sine, SIGN. So the sine probably alternates sine, SIGN. So the next one's probably a minus. X cubed, what do you think the coefficient is? 3 factorial. Okay, so this is a big whopping guess. We have no idea if this is true. But we have a hunch. Plus x to the 5th over 5 factorial minus ... Okay. Now those are odd numbers, right? Just a note, odd numbers can be written as either 2n plus 1 or 2n minus 1, depending on where you start counting. Since we usually start counting with series at 0, then I would probably pick this guy if n starts off with 0. If we started off counting with n equals 1, we'd use the other one. Your call. Let's graph this to see if it actually looks reasonable. I happen to have fired up GeoGebra here. And on GeoGebra, I am going to graph x minus x cubed over 3 factorial, which is what? 3 times 2 is 6, plus x raised to the 5th divided by 5 factorial, which I'm pretty sure is 120. 3 terms, graph. Ooh, that's a funky graph. Let's blow that up. Options, font size, 20. I zoom in there. Oops, move. Okay, so that kind of looks sine-y right in here. Right? Let's graph the sine of x and see. Hey, look at that.
Son of a bitch.
Okay. Now, what if I add more terms? You think it'll hug it longer?
Yeah.
Yeah. So let's add another term here. So double click, add a term. What's the next term going to be? Plus or minus? Minus x to the 7th. Oops. Whoa. Divided by 7 exclamation point. Enter. Ooh. We could add another one. That was a minus. This is a plus. X to the 9th over 9 factorial. Okay. That is wicked cool, isn't it?
Very cool.
It is amazing. Taylor series are lovely. Yeah. And so we could keep adding terms and we keep hugging it more and more. We guessed right. How would I prove it? That's just a guess. Ooh. Okay, so Jeff brought up the point that sine is the cosine shifted pi halves to the right, which is true, yeah. So that we could substitute for x minus pi halves in the series for the cosine. Ooh, let's write that down. Let's see. So that's not quite what I was going to do, but it's an excellent tangent.
I don't know if
Okay, so we are instead going to write cosine of x minus pi over 2, because that takes the cosine and shifts it to the right pi over 2, which should give me the sine. Is that right? I think that's right. So that means in here I have to replace each of those. 1 minus, now here I'm going to have x minus pi over 2 squared over 2 minus x minus pi over 2 to the 4th squared over 4 factorial. Okay. And this supposedly should equal the sine of x. Now wait, that's supposed to be a 4th power right there. This has even powers. Thank you, that's correct. Now the problem here is this has even powers. The sequence we guessed at a moment ago has odd powers. So what we have here, this thing right here appears to be a power series. I'm not calling it a Taylor series at the moment. Power series centered at what? Pi halves. Yeah. Okay. A Taylor series is a special kind of power series, one which you use derivatives of the function to create. We haven't done that yet. Okay. But we did play around in section 10.7 that you can do substitutions on a known power series to create a new one, which is what Jeff suggested here, which is a great idea. That's a good review of section. Now the cosine, oh, this is a good one. The cosine converges to all real numbers. We shifted this pi over 2, so what do you think the convergent interval is here? Yeah, it doesn't matter if you shift infinity pi over 2 left or right, it's still infinity. Yeah, so it's still all real numbers. If the interval was finite, but had boundaries that were finite, then we would have to worry about it. Yeah. Okay. So here's what we're going to do. We're going to develop the series by hand. Develop. So we got a little more work to do before we can get back to the integral of sine squared, but we'll get there. We're going to develop the series for the sine. To do that, we have to take repeated derivatives. And what I like to do is I like to make a table. And in my table, I have n goes 0, 1, and 2, and so on. I'm going to have the function's nth derivative in one column. In another column, I'm going to have the nth derivative evaluated at the center. In this case, the center is 0. We'll do centers non-zero in a minute. And then I want to take whatever that result is and divide by n factorial. And that will help me discover the coefficient so I can discover the power series. Okay, let's see. The original function is line 0. That is the sine of x. And its derivative is the cosine of x. And its derivative is negative sine. And its derivative is, and then it goes back to sine, and we're going to repeat this pattern. Okay, so that's kind of cool. We're repeating that pattern. Good. I think we've taken enough derivatives. Okay. Now, again, we're doing the trig functions right here. They do have repetitious patterns. Most other functions don't. All right, then we plug in 0. Sine of 0 is 0. Cosine of 0? 1. 0. Negative 1. 0. The next one would be 1. Pattern continues. Divide by n factorial. Well, this is still 0. 1 divided by 1 factorial is 1. 0. Negative 1 over 3 factorial. 0. The next one would have been the 5th step. Positive 1 over 5 factorial. And those look like the coefficients we invented by guessing. Cool. Now, just like we proved that the cosine using the remainder theorem converges for all real numbers, we could do a similar proof for this. It's actually the exact same proof, pretty much. So we're going to skip that, and we're just going to use this series. Okay, so here's what we know. We know now that the sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And we could keep going, right? Minus x to the 7th over 7 factorial. The summation notation, if I say this is term 0, this is term 1, term 2, and term 3, for odd numbers, then we would use 2n minus 1. So this would be equal to the sum as n goes from 0 to infinity of -1 to the n over 2n minus 1 factorial to the power, and then in the top would be x times 2n minus 1. So that's the most common version of the sines Taylor series. Okay. Now I prefer to call it a Taylor series. Since the center here is 0, the author would call it a Maclaurin series. So just note, if the homework says find a Maclaurin series, what is your center? Yeah. Yeah. It could be, center could be anywhere. Yeah, so the next problem will have a different center. Okay, now what we're going to do is we're going to use this to find the integral of the sine squared of x, sine of x squared, dx. Now to do that, we got a couple of steps. First thing we need to do is in the red series, we're going to replace x with x squared. So let's make that black as an intermediate step here. The series for the sine of x squared is going to be x squared minus, let's see, what is x squared cubed? Almost. X to the 6th. Yeah, so we're going to replace that in there. So that's going to be x squared cubed, which is x to the 6th, over 3 factorial, plus, let's see, x squared to the 5th. X to the 10th, yep. So that would be x to the 10th over 5 factorial. And we'll write one more term, x to the 14th over 7 factorial. And it just keeps going. Well, in section 7, we learned that we can integrate term by term a convergent power series. So now we're going to integrate both sides. Okay. So the integral of the sine of x squared dx is going to be equal to, now when we integrate, we get a positive constant. Plus the integral of x squared is what? X cubed over 3 minus x to the 7th over 7 times 3 factorial plus x to the 11th over 11 times 5 factorial. And I think I can squeeze one more here, minus x to the 15th over 15 times 7 factorial, and keeps on going. Now, since we don't have any boundaries on this integral, we cannot determine what c is. If we decided we were integrating from 0 to some other number, then we could find what c is. But at the moment, we're just going to leave it there. So, although we can't write the integral of the sine of x squared as a fundamental function that we're used to writing down, we can find its power series. And the power series, in this case, what was the radius of convergence of this original red series up there? It was infinite, all real numbers. So this series we just generated should also be convergent for all real numbers for this integral. So now somebody says, I need you to calculate the integral of sine of x squared, and then they actually gave me boundaries. I can approximate that to whatever degree they want me to, because I also have a remainder theorem to go with this. And I can even estimate how far I'm off in the definite integrand. Okay. Yes.
Yes.
The point is, we now, between Taylor series and what we know about power series, have the ability to generate solutions where we could not before. So if we were solving some engineering problem, and in that engineering problem, this integral came out, before today, we were screwed. We had no tools to do that with. We just throw up our hands and say, this is not solvable. Now it is. And because of the remainder theorem, I can get you as close an answer as you need me to get. You say, I need an answer to the nearest millionth, I will be able to figure out how many terms to add to make that happen. Maybe, maybe not. Now the other nice thing is we programmed computers to do this, so the computer could do it for me. Okay. But this is the math behind how a lot of approximation methods work. Okay. And here's the more exciting thing. There are much more advanced approximation techniques than these here, because some series converge slowly. The factorials converge rapidly, so this one's not one of those. But very clever people have found better ways to make approximations of things like this. But we are just scratching the surface of how those kinds of things happen. All right, we need to take a 5-minute break. And I'm going to start a new recording. Oh, my glasses are stuck. So let's see. William is still there. William, I'm going to stop and restart this.
No, you're fine. I could actually get through.
Jeremy, I will re-invite you to the new one.